In chemistry, we do a lot of measurements and we pay a lot of attention to units and numbers and calculations. And when we do calculations in measurements, we're commonly going to be using the metric system. Now, the metric system is what we routinely call it, but really this is the same thing as the SI units. SI stands for Système International. I don't speak French very well. And so this is the International System of Units. And it would be nice if everybody did use the metric system because then we'd all be super comfortable with it. But in reality, in the United States, we usually use some different units, some of them based on old English units. But let's go ahead and take a look at a couple of tables from our book to get familiar with the metric units and all of the prefixes that go along with them. We have several base SI units, is what they're called, depending on which quantity we are measuring. So over here on the left-hand column, these are the base measurements that we might be able to make, the quantities or dimensions that we are measuring. And in chemistry, we almost always just focus on these first four: mass, length, temperature, and time. And really mass, temperature, and time are way more common than length, but we do use length. And then amount of substance, which we use and we'll talk about in a little while. So for the most part, we aren't going to need to worry about electrical current or luminous intensity. But we have kilogram, meter, Kelvin, second, and mole that we are going to be paying attention to as our base SI units. And then we're going to be modifying these base SI units with prefixes that allow us to look at factors of 10 that are either larger than or smaller than one of the base unit. So let's take a look at that table too. I should have really said table also because it's table 1.1 in our book, and the other one was table 1.2. So when we go to the middle of this table, we can see it doesn't even have the 1 place. That would be the undecorated unit in there. And the interesting thing about mass is that kilogram is not the unmodified unit. The gram is the one that we are modifying in order to make a kilogram. And so 1,000 of the base unit gram, which is not the base SI unit, gets us the kilogram, which is the base metric unit. So it might be simpler to think about a meter instead. That when we are thinking about a meter, we have 1 meter. If we go to 1/100th of a meter, then we have a centimeter. If we go to 1,000th of a meter, then we have a millimeter. And if we go higher than a meter, everybody probably has a pretty good sense for what a meter is. It's a little over 3 feet. If we hold our hands out past our shoulder width, but not at our full extension, that's about a meter in front of us. So if we are looking at these quantities here, we can see a kilometer is 1,000 meters, and most of us have a pretty decent sense for what a kilometer looks like, or if you don't really have a good sense for it, maybe you have run a 5K race, which is a little bit more than 3 miles. So again, here we are doing some unit conversions, which we're going to talk about a lot. Now, when we look at this table of SI units, some of these, it says, are commonly used. I don't think I've ever used a zeta as the prefix here, so quite a few of them are a little bit less than common, but they do allow us to deal with very large numbers or with very small numbers in a fairly convenient way. So we can put a prefix on here. For example, some lasers work at a femtosecond speed. And so it would be really kind of irritating to have to write all of these zeros to indicate how many seconds were present in how quickly this laser pulsed. And we have lots of light that is in the nanometer wavelength. And so 10 to the 9 is much more convenient to write than all of these zeros. So we use these prefixes in order to pay attention, to simplify our life with a lot of the other units. Now, you will not need to memorize all of these units. So let me write down a short list of which ones you need to know. So you need to know kilo, which is 1,000 times our base. You need to know centi. You need to know milli. You need to know nano. First, you need to know micro. I'm just going to switch to 10 to the minus 6. And you need to know nano. And sometimes you might need to know pico, but mostly not. Okay, so if you happen to be able to remember these 5 metric prefixes, you will be totally fine for our class. So for Chem 141, this will be enough. If you need any other ones, you can just look them up, but I do expect you to just know these ones. Now, of course, what's interesting is that in other places of the world, it's very common to use metric system. And a couple of years ago, I got to do a Fulbright in Hungary, where I lived there for 6 months. And I went and realized that they use decagrams. Let's go back to that table. So here's our table. There's deca. They use decagrams when you go to the deli in Hungary and you want to order something. Most places that I have traveled, they use kilograms. And so I'm pretty comfortable with thinking about kilograms. I know there's about 2 pounds per kilogram. So if I'm thinking about how many kilograms of apples, I think, okay, I'm probably going to start with half, right? That's about a pound. Okay, so decagrams was totally challenging for me to remember. So a decagram is 10 grams. So if I wanted to order a half a pound, I needed about a pound, I needed about 45 decagrams. So this was a challenge for me. I always had to go to the deli and think, okay, what's that unit conversion again? Okay. So all of these units and this kind of discussion of unit conversions leads us to our next section. When we are doing unit conversions, it's because we want to do calculations that will be able to simplify our life, or it's because we are in an unfamiliar unit that we don't sort of mentally understand, and so we're going to convert it into something else that works for our brains better. So, for example, when I was in Hungary and I was thinking about decagrams, I had to sort of mentally convert into pounds so that I could get my head around it. So in order to do these unit conversions, we're going to do dimensional analysis. And dimensional analysis is really awesome because it just uses units to make sure that our answer is the right answer. We're using it to keep track of what's going on in our calculation. And dimensional analysis is super cool. It relies on 2 main awesome math factors. Okay, one of them is the highly underappreciated but incredibly amazing equal sign. And the other one is the power of multiplying by 1. Okay, these sound kind of dumb when I write them like this, but it's only because we've gotten to this point where we don't even think about what an equal sign means anymore. So let's look at an equivalency. That's what an equal sign means. It means 2 things are exactly identical on both sides of my expression. So let's think about 1 inch, which if I look up how big an inch is on a ruler, for example, and I think about it in terms of centimeters, which would be one of our metric units instead, 1 inch is 2.54 centimeters. So from algebra, I know that if I divide out the same thing into both sides, I have scaled that thing in an equivalent way. And so I haven't made any significant change to the system. But I also know that if I divide something by itself, for example, if I divide this 1 inch by itself, not only have I not changed either side because I divided by the same thing, I also divided by 1, which doesn't change anything, but it doesn't matter if this is a 1. But these two things cancel each other out because it is one thing divided by an exactly the same thing, which is the same as unity. It is 1, right? That is this number right here. And this equal sign that I'm about to circle in red because it's super exciting and important, this equal sign means that 1 is exactly the same thing. I shouldn't use these two double lines because then it looks like another equal sign. Sorry. Here we go. 1 is exactly the same thing as the ratio of 2.54 centimeters divided by 1 inch. And so that means that if I have some other number, like, for example, 18.3 inches, then I can multiply it by 1 in the form of 2.54 centimeters divided by 1 inch, because that's equal to 1. If I multiply these two things together, then I'm not changing this by a factor. It's not like I'm multiplying by 2. It's not like I'm dividing it in half. I haven't changed the quantity. So if 18.3 inches is this long, I have not changed the amount of space that this distance takes up when I multiply it by 2.54 centimeters divided by 1 inch, because this is the same thing as 1. And so I know this doesn't change by the incredible power of multiplying by 1. So if you type this number into your calculator, go ahead and pause the video and do that really quick. Okay, you get to check my work here because I didn't have my calculator handy, so I did it by hand. So, and I haven't done multiplication by hand with decimal places in quite a while, actually. So, anyhow, I calculated it out and I got 40.4 centimeters, and hopefully that is true. Now, how did I know that I needed centimeters? Well, it's because I also know that when I have inches divided by inches, those two units are going to cancel out the same way that they did right here. The units are labels for this number, but they also can do math with each other. So when I did this calculation, I actually used my common sense here to say, okay, is this answer a reasonable answer? And I thought to myself, well, this is like 18, and this is sort of like multiplying by 2, only a little bit more than that, right? And so if I take 18 by 2, I know that's 36 if I multiply those. So I should have a number that's a little bit larger than 36. And this is a little bit larger than 36, so I'm pretty sure that I did my math right, but you can always let me know if I did not, and then I'll go and make a correction. All right, so this is an example of us doing dimensional analysis, and when we get done, we know that 40.4 centimeters takes up exactly the same amount of space as 18.3 inches does. So when we do dimensional analysis, we are not actually changing the number in any way except by the unit that we happen to be labeling it with. So usually the reason why we do this is because we have different units, we need to convert them all into the same unit, or the unit that we have is not as convenient as some other one because maybe we have some some other unit that's going to cancel out later. So that's usually why we do it. And we're going to get lots of practice doing unit conversions. So hopefully you will feel super comfortable with that really soon. Okay. Now, we've talked about some dimensional analysis, and I want to talk a little bit more about measurements as well. So when we take a measurement, we are going to have some kind of a unit unless it's a counted number. So, for example, if I look around the classroom, I might count 14 students in the classroom. That is an exact number. I might label 14 and then student would be my unit here. But I might also just say how many students are there? There are 14. But anytime we take a measurement and we use some kind of a measuring instrument, we're probably going to have some unit. So we need to label our numbers with units. I made the mistake of telling my 6-year-old son this summer that we have no naked numbers. No naked numbers. Every number needs a unit. And he thought that was really super hilarious. And so now he goes around every now and then saying, no naked numbers. So hopefully you will remember, no naked numbers. Always put the units on, assuming that there are units. The other thing that we need to pay attention to is how many digits can we reasonably record when we take a measurement. Now, if you're taking a mass on a balance, the digital readout just tells you a number and you write it down. And that's totally fine, and that's valid. All of those digits that you see on the mass balance are going to be valid. But let's think about doing some other measurement. So, for example, this summer I measured volumes of water. And I used 3 different instruments. I used a beaker to measure, it was a 50 ml beaker, but I was measuring 10 milliliters of water. And there was a little line there. And then I also had a graduated cylinder. It was a 10 milliliter graduated cylinder. And it had gradations, as you would expect, more than what I've drawn here. And then I had a volumetric flask. And if you haven't used a volumetric flask before, volumetric flasks are this kind of funny shape here, and they have a fill line. And so the idea is that you fill up whatever your liquid is just up to the fill line where the meniscus just touches where that fill line is, and then the volume contained in that is exactly what you were supposed to measure. Okay, and so I used a 10 milliliter volumetric flask. The way that I measured the actual volume of the water here was I filled up each container up to its 10 milliliter mark to the best of my ability, and then I weighed it. I took the temperature of the water and then I calculated what the true volume was from the mass, right? Using density. Density is equal to the mass over the volume. So I just did a little bit of rearranging here and solved for volume is equal to mass over density. So I multiplied by the volume and then I divided out the density. And the idea is that the density depends on the temperature of the water. So we measured the temperature of the water and then we looked up what the density was in a table. So I'm going to take you to my Excel file where I recorded all of those data. Okay, here we are. So here's my temperature. Here's the density that I looked up from a table. And then here's all of my raw data. I measured the empty mass of the beaker, the mass with the water, and then I subtracted one from the other to get the masses of the water, and then I calculated what the volumes were. So if we look at the volumes of the water in the beaker, you can see that they were all pretty close to 10. One of them I got spot on, but most of them, there was some variation. Let's see, I'm going to scroll this over here so you can see the last of the measurements, right? Most of them were around, 9.9. You can see my average value was 9.85 milliliters, so that's not too bad. Now, with the graduated cylinder, I did the same exact thing. I had a slightly different temperature, so I had a slightly different density. And when I calculated the volumes of the water, you can see they were quite a bit lower. I was much closer to about 9 milliliters, in the volume of the water for this graduated cylinder. But you'll also notice there's a lot less scatter, that all of my numbers are much more closely clustered toward each other. So over here, I had a range from 10 down to 9.7 0.61. So that's a pretty big range, right? Almost 0.4 milliliters of difference. Now over here, I have a range of 9.09 down to 8.99. So that's 0.1 milliliter. So 1/4 of the spread with the graduated cylinder. So my numbers were much more closely clustered together. And then finally, with the volumetric flask, you can see that my numbers were even more closely clustered together. So they were all much closer to 10, and my high was 10.08, my low was 10.02. So 0.06 milliliters was the maximum distance between my top and my bottom number. So these numbers were much closer together than they were before. So these data illustrate a couple of different things. One of them is that I probably shouldn't record the same number of decimal places for my average mass for my beaker, or excuse me, my average volume for my beaker, compared to the average volume from my volumetric flask. I probably can't claim 2 decimal places on here because I had so much variation in my numbers. Second, I want you to notice that because these guys have much more of a spread, these don't have the same precision. So now it's going to be time for me to record what I'm talking about here. So let's look at what precision is. All right. So precision is when multiple measurements, maybe I should define this slightly differently. To be precise measurements are when we get the same answer every time. Or the same measurement, I should say. So the closer they are together, the more precise they are. So if we go back to those Excel data, you can see that my volumetric flask data were more precise than the graduated cylinder, and the graduated cylinder data were more precise than the beaker data. So none of them were what we would call, 100% precise. We didn't get the same answer every single time when we did the measurement, but we got very much closer with the volumetric flask. So the volumetric flask was more precise than the graduated cylinder and more precise than the beaker. So that's precision. The other thing that we get when we think about precision is how many significant digits we can keep. So this informs us how many significant digits we probably can reasonably keep. Now, what is a significant digit? A significant digit is a measurement that has meaning. So if I go over to my data again, because I have a fairly large uncertainty in that last decimal place, this last decimal place, like this 6 here, is probably not a significant decimal place. It probably would be more honest for me not to claim that decimal place as a real measurement. Now, because I was measuring masses, I can really keep it. But if I'm talking about volumes, then if I'm talking about my average volume, I'm probably going to say, I'm just going to drop that last decimal place there just to be a little bit more honest about how well my beaker measures 10 milliliters. So when we are talking about significant digits, if we spend a lot of time taking really careful measurements, then we're going to get probably better significant digits than otherwise. But The other thing that we need to pay attention to is accuracy. So when we are doing accurate measurements, these give us the correct answer. Well, what was my correct answer? If I look back at those Excel data, I could have to remember that I was trying to measure 10 milliliters. So if I look at the volumetric flask, all of my measurements were quite close to 10 milliliters for my volumetric flask. But my graduated cylinder was not great. I really got reliably about 9 milliliters when I was trying to measure 10. So whereas I would say that the volumetric flask is fairly accurate and precise, I would say that the graduated cylinder is somewhat precise, but not accurate, not very accurate. And the beaker, it had quite a bit of scatter here, but it was fairly close to 10 milliliters. So I could say that it was fairly accurate, but not very precise. So we can have measurements that are accurate and precise, one or the other, or neither. So what I want you to take away from this conversation about precise measurements and accurate measurements and significant digits is that when we take data, we need to pay attention to all three of these things. And so if we record significant digits that are informed by precision and accuracy, then if you are doing measurements, additional measurements and calculations with those data, you want to pay attention to those significant digits and actually, respect the fact that you put a lot of effort into, or somebody put a lot of effort into taking these measurements and getting these significant digits. So please make sure that you keep significant digits appropriately. I have a separate video that talks about significant digits and identifying them. So take a look at that one if you need a little help. I also have the summary sheet that I use in the video and kind of go through it. I've posted that to our Moodle as well for you to use as a resource. Now, we're going to be doing a ton of calculations that rely on you paying attention to significant digits and units and often looking at measurements, but it also requires a lot of problem solving. And our book has a little acronym that they use called COAST that recommends a method for working on problem solving, so a strategy for thinking about problem solving. And this, if you're feeling stuck when you're doing problem solving, this is not a bad way to start. So COAST, the first two letters stand for collect and organize. So you're going to read through a problem. You're going to identify what all of the numbers are, all of the different measurements are that you have, all of the pieces of information you have, and you're going to collect them all together and put them in some kind of an organized way. And I often draw pictures at this point. I find it very helpful. And I will model this when I do problem solving in front of you in class. The A stands for analyze. Think about what kind of information you have and try and figure out how do the pieces fit together. Do I need to look up any additional information? Constants, unit conversions, things like that. Try to find out how they fit together and use them to come up with a strategy for how to solve the problem. And that's what comes next. S is for solve. Hopefully you will always get to this step. If you have any trouble, please reach out to me about it. But even after you solve the problem, then you need to think about it. So just as when I did that multiplication problem on paper, I thought about my answer to make sure that I understood whether or not it made sense. And so these are some questions that you can ask yourself. You can say, does it make sense? Did I get a number that is reasonable? If I'm calculating mass and I get a negative number, it's probably not going to be correct unless I was measuring how much mass I lost or something like that. So, use a reality check there. So you also need to ask yourself, did I find the number that I was looking for? Which might be another way of saying, did I finish the problem? Because sometimes problems have multiple steps. And so, we get to the first answer and then we need to move on and see whether or not there are additional ones. You can ask, do I have the correct units? Because I might have asked for an answer in grams and you might have had it in kilograms. How about sig figs? Do you have the correct sig figs for the problem? And I'm going to tell you here that these last two, I take off points for these all the time. And I will be strict about these. I will also write notes on them, and I would be happy to talk to you about them every single time, anytime, to explain them. But please have a lot of care and use attention to detail here to make sure you check that you have units and that they are correct units and that you have correct significant digits. And then the last thing to think about is, can you check your work? All of these were in my point of view, so can I check my work? So if you can check your work and you can verify that your answer makes sense, that you have solved for the problem that you need, and that it has the correct units and the significant digits, so you're probably going to be correct. I'm going to model this a lot, and we're going to practice this a lot, and so hopefully everyone in this class will get super comfortable with doing calculations. And as always, please reach out to me at any point, and also know that we have wonderful tutors both in math and in science who are ready to help you at a variety of times. And so please use the resources that we have here.